Inorder Traversal. Inorder Traversal is a type of depth-first traversal technique in which you visit the left subtree first, then you visit the root, and after that you visit right subtree. So this is the order of traversal in inorder. In the previous lecture, we learned about pre-order traversal, and there we had seen that first you will go to the root, then you will go to left subtree and then the right subtree. Also, we discussed that pre, in and post. What is this decided on the basis of? This is decided in the basis of the position of root. So pre means before, post means after, and in order means rightly in the order. So in case of pre-order, root comes before left and right subtree, and here we are considering in order. So in order, root comes right in between left and right subtree. So that is during traversal. Let us see how this traversal is done with an example. So it will be easier to understand with an example. So just keep this order in mind. First you have to go to the left subtree, then the root, and then you will go to the right subtree. This is the order we will follow in order traversal. What we'll do is, we'll take the same tree that we took, for example, in pre-order lecture, so that it will be clear for you what exactly is the difference between the sequence in pre-order and in order. So this is the tree we used in pre-order lecture. A, then A has two children, B and C. B again has two children, D and E. And what about C? C is having only right child, which is F. C is not having any left child. This is the tree we used for pre-order traversal. So here we are going to do in-order traversal. So in pre-order traversal, what is the order we got? We got A, then we visited B, D, E, C and F. So this is the pre-order traversal order we got. This is pre. So here we are going to consider in order. Let us see what is the difference in order when we do in order traversal. So in order, what is the rule? Left, then root, then right. So first you have to go to the left subtree, then the root, and finally right subtree. So when I say left subtree, it is this complete subtree, and similarly when I say right, it is this complete right subtree. So let us start with it. First you have to go to left subtree. So can I write B? Is that right as the first entry? No, it is not right, because it is not just one node B. Instead, it is about the whole subtree. So you have to go to the left subtree and then apply the same in order rule in the left subtree. So how will you apply it? Go to the left subtree, again mark left, root, and then right. So now in your left subtree, there is only one node. So whenever there is only one node, you can stop there. So you have only one node, so you can directly write the entry D. So D is my first entry and I have visited D. So what is the rule? After left subtree, you have to go to root. So go to the root next. What is the root now? It is B. So B is written. After B, you have to go to the right subtree, which also has only one element, E. So you can directly write E. E is also visited. So I am already done with D, B and E. What is the next thing? So my left subtree of my whole tree is completed. Once left subtree is completed, I'll go to root. Root is A. So A is also visited. After A, I'll go to the right subtree. In the right subtree, I'll again mark left subtree, root and right subtree. So left subtree is empty. For C, there is no left child. So the left subtree of C is empty. So I'll go to the root. Root is C. So C is also done. And after C, I have to go to right subtree, which has only one node, which is F. So I'll write F. So my in order traversal is D, B, E, A, C, F. So this is the order. So if you see in pre-order, you got this order A, B, D, E, C, F. And in order, you got a different order. So this is how these differ. So in the pre-order lecture, we had discussed about a hack, a technique in order to directly find out this order without actually going through all these steps. So similarly, in Inorder, is there any hack? So yes, there is. So see, you have to technically be very clear on what exactly is Inorder, what is the rule, what is the logic of deriving. But if you want to directly find out what is the Inorder, there is a method. The method is like this. So in pre-order, what is the method? You simply have to go from one side of the tree and write whichever node you are getting to see, right? So if this pre-order, we obtained it as A, then B, D, then E, C, F. This is how we obtained pre-order. In order to obtain in order, you use a very similar technique. The only difference is this time, with whichever is a leaf or doesn't have any children, you just put two strokes like this on those. This is because we need to understand whether it is the first visit, second visit or the third visit. So in order to differentiate between the first, second and third visit, I am putting these extra links wherever there is no child. So now the rule is I have to again start from here and traverse the same way I did for pre-order. But instead of writing down the node whenever I see a node, this time what we have to do is we should write down the node only when it is the second visit of that node. So let us see by writing on the second visit. This is the technique you have to use in order to find in order. So here is the in order sequence of this tree. You start from A, first visit, B is also first visit, D is also first visit. You keep going on. So till you reach second visit. This is first visit of D. Now you came back. This is the second visit. So now you know why I gave this extra horn here. Because with that, I am able to identify that this is the second visit of D. So in second visit, I'll write it down. D. So now it is the third visit. This is the second visit of B. In second visit of B, I'll write down B. So after this, I'll continue. First visit of E, second visit of E. Whenever it is second visit, I'll write it down. Again, I'm going through third visit of E, third visit of B, second visit of A. So when it is second visit, I'll write it down. First visit of C, second visit of C. So I'll write C. Again, I'll come down. First visit of F, second visit of F. So I'll write F. Then I'll go through third visit of F, third visit of C, and third visit of A. So I got the order D, B, E, A, C, F, which is exactly same as the in order sequence. So whenever you want to find the in order sequence, easier method is this. Just go through the tree. Whenever it is the second visit, note down that node. So this is the hack. So you logically understood how to find out in order. Also, you also know the hack if you want to directly find the in order sequence. So what is the next step? We need to identify what is the pseudocode, and then we have to see time and space complexities of the pseudocode. So we are going to write the pseudocode. So just keep the logic in mind that you have to go to the left subtree first, then the root, and then the right subtree. So when I say root, I have to visit the node. Okay. So let us try to write the pseudocode. So we are writing the pseudocode in order of node. So here we'll start with the root always. So what is the base condition? That is, when this is, we are going to write a recursive algorithm. So recursive algorithm always need a base condition. What should be the base condition? When should you stop? Whenever this node is null. Whenever the input is null, you don't need to do any more traversal. So if your node is null, what will you do if it is null? You have to simply return. So whenever it is null, you can return. Now let us see what are the steps we have to write. What are the logical steps? First you have to go to left subtree, then you have to go to the root, then you have to go to right subtree. This is the logic. So how will you go to the left subtree? You have to recursively go to the left subtree. So presently I am at node. So I'll call the same function in order. I'll call in order of node pointing left. So I'll go to the left subtree. That is, whichever node I am in, I have to go to the left node and then call the same function and ask it to continue the same process, right? So this is how I'll call left subtree The next step is I have to print the root. How will you print the root? Simply print node. Okay. So this is visiting the root. The next step is going to the right subtree. How will I go to right subtree? I'll do in order of node pointing right. So this is how I'll go to right subtree. So this is the recursive algorithm which will run in-order traversal. Okay. So let us understand this algorithm, understand its time and space complexity and a dry run. So first of all, what is the time complexity of this algorithm? Coming to time complexity, what is the whole purpose of this traversal? We are going to go through all the nodes of the tree, right? This is the whole purpose. We have to visit each node exactly once, that is traversal. So when you visit each node exactly once, your time complexity will be order of n. So if you have n nodes, time complexity is order of n. What is the space complexity? So same as the case of our pre-order traversal, space complexity is also order of n, and the reason for this is you are using recursive stack. So in the recursive stack, when you call it in case of a skewed tree, that is if tree grows like this and all the n nodes are directly linked as a left child to the next, or it can also be like right child. Either way is called skewed tree. So if it is a skewed tree, recursive stack will fill up n entries. So that is how it will be order of n, the space complexity. That is, while running this algorithm, it will take up that much time, that much space. So let us just see how this is done. So what we'll do, we'll mark this is step number 1, this is step number 2, printing is step number 3, and going to the right subtrees, step number 4. And let us just draw the tree here. What I'll do is, step numbers I'll put on the other side. I'll draw a line here. Step number 1, 2, 3 and 4. So I'll draw the tree here. A has 2 children, B and C. Again B has 2 children, D and E, and C has only one child, which is F. So this is my recursive stack. In the recursive stack, what I'll do, first I'll call in order on the root. That is, always your algorithm will start from the root. So in order of A, what will in order of A do? I'm going to the first step. So it will check whether it is null, it is not null. So I'll continue to the second step. In the second step, it will call in order of node pointing left. So what is A pointing left? A pointing left is B. So I'll call in order of B. So this is already done with the second step. So third step is remaining for in order of A. Okay. So I reached in order of B. First step is checking whether it is null. So I checked it is null. It is not null. It went to the second step. In order of node pointing left. Node pointing left of B is D. So I'll call in order of D. Once I call in order of D, I'll go to the third step. But do I execute third step? No. I'm just keeping it in mind that after I complete D, when I come back to B, I have to execute the third step. Okay. So in D, I'll execute first step. I'll check whether it is null. It is not null. I have to go to node pointing left. What is node pointing left of D? Left of D is, there is nothing in the left of D. So which means it will call in order with null entry. So when it is null, in the first step itself, it will return and come back. So this entry will be popped off. After this is popped off, I'll again go to D. What is the third step of D? In third step of D, I have to print the node. So I'll print D. I have printed D. After I print D, I'll go to the fourth step, which is node pointing right. So what is D pointing right? There is nothing. It is null. So again, I'll put null. I'll push into the stack. In order of null. What is in order of null? When it is null, you have to return, which means I have to pop it off from the stack. After I pop it, I'll go to D. So all the steps are completed. I can pop off D. So I pop D off. So I reached B's third step in order of B. So what is the third step? Third step says print node. So I'll print B. So I'll go to the fourth step of B, which is B pointing right. B pointing right is E. So I'll call in order of E. So fourth step is done. So all the steps are done for B. B is there in the stack because I have to complete E. Then only I can pop off B. Because E is called from B. It is rightly in the fourth step. So in the first step of E, it will check whether E is null. So E is not null. So it will go to the second step. Second step says E pointing left. What is E pointing left? There is no left child. So it is null. So I'll call in order of null entry. So whenever it is null, I'll return. I'll pop this entry off. Then I'll go to in order of E. I'll print it because it is third step. Third step of E is print node. So I'm printing E. After I print E, I'll go to the fourth step, which is E pointing right. E doesn't have a right child, which means I can put in order of null. Right is null. So because it is null, it will be popped off. Then I'll come to E. E is already done. E will be popped off. B is also done. B will also be popped off. I reached A. In A, I have to execute third step. So third step is print node. So I'll print A. After I printed A, I have to go to the fourth step. Fourth step says in order of node pointing right. So what is the right node of A? It is C. So I'll call in order of C. So A is done, but after C only I can pop off A. So in C, I'll execute first step. If it is null, no, it is not null. I'll go to second step. Second step says C pointing left. What is the left child of C? C doesn't have a left child. C only has right child. So left child is null. So when I execute second step, that is node pointing left, it will be null. So in order of null entry. In order of null will be popped off. Then I'll come to third step of C, which is print node. So I'll print C. After I print C, it will go to fourth step, which is in order of node pointing right. What is right child of C? It is F. So I'll call in order of F. So C is also done, but I can pop off only after popping F because this is a stack. In stack, you have to pop the top entry. After that, you can pop the next entry. So in order of F, again checks whether it is null. It is not null. I'll go to second step. Second step says in order of node pointing left. F doesn't have a left child, which means it is null entry. In order of null will be popped off. Then I'll go to the third step, which says print node, print F. So I'll print F. Then what I'll do? After printing, I'll do the fourth step, which is in order of node pointing right, which is also null. So in order of null, this will be popped off. F is also done. F will be popped off. C will be popped off and A will be popped off. So my complete algorithm is done. So in this algorithm, what you can notice, one, you got the in order sequence. Second thing is how the stack was used. So depending on the height of the tree, the stack size will also be decided. Maximum stack size possible, that is the maximum memory that will be used by this algorithm in recursion stack, is same as the height of the tree. So in this case, this is a balanced tree, so height will be of the order of log n. But in worst case, your tree can grow like this. You can have A, then B, C, D, so on. Then the height will be order of n. So in worst case, it will take order of n space. So time complexity is order of n because you have to visit all the n nodes. Space complexity is order of n because in worst case, it can be a skewed tree and the recursion stack can take up all the n entries. That is why space complexity is order of n.